long-range ballistic missile activity raises to priority attention the mastering of high-altitude burst effects phenomenology.
On August 1st, 1958, 11 minutes before midnight, the sky above Johnston Island in the Central Pacific suddenly turned white. A 3.8 megaton nuclear warhead had just detonated high above the Earth during Operation Hardtack Teak. The flash was visible from Hawaii. In Honolulu, more than 700 nautical miles away, police switchboards were flooded with calls from frightened residents asking what they had just witnessed. Thousands of kilometers south, in western Samoa, the explosion produced an artificial aurora 4 times stronger than anything created by natural solar storms. But the true danger of that night was not the light. It was the silence that followed. The nuclear blast had injected massive amounts of charged debris into the ionosphere, the fragile, electrically active layer of the atmosphere that radio communications depended on. For 9 hours, high-frequency signals between the Pacific and Australia went completely dark. Air traffic controllers in Honolulu lost contact with aircraft. At the Pentagon, officers waited anxiously as hour after hour passed with no communication from the test site. When the first message finally came through, it was simple. "Are you still there?" The implications were terrifying. In 1958, nearly all long-distance communication depended on 2 systems: submarine cables or the ionosphere. Cables could be cut. The ionosphere, as the test had just shown, could be wiped out by a single nuclear detonation. In a real war, the Soviets would not need to destroy American infrastructure. A few high-altitude explosions could collapse global communications entirely. Military planners faced a question that sounded almost absurd. If the natural ionosphere could be destroyed, could humanity build its own? At MIT's Lincoln Laboratory, engineer Walter E. Morrow Jr. proposed a radical solution. Instead of relying on a fragile natural layer, the United States could create an artificial one, not through chemistry or weather control, but through pure geometry. His idea was to launch hundreds of millions of tiny copper dipoles into orbit, forming a reflective belt around the planet. Radio signals could bounce off this artificial ring, allowing communication even if the real ionosphere was disrupted by nuclear war. The plan was called Project Needles, later renamed Project West Ford. It would become one of the most controversial experiments ever conducted in space. The specifications were astonishingly precise. Each needle had to be exactly 1.78 centimeters long, half the wavelength of the 8 gigahertz microwave signals they were meant to reflect. If the length varied by even a fraction of a millimeter, the physics would fail. The needles had to be thinner than a human hair, with diameters measured in micrometers. In total, 480 million copper needles would be launched into orbit. Yet together, they weighed only about 19.5 kilograms, less than 50 pounds of metal to create a reflective belt around the entire planet. The deployment system was equally ingenious. The needles were packed into blocks of naphthalene, the same chemical used in mothballs. In the vacuum of space, the naphthalene would sublimate, turning directly from solid to gas, and release the needles. Solar radiation pressure would then spread them into a thin ring about 8 kilometers wide and 40 kilometers thick, circling Earth in a polar orbit between 3,500 and 3,800 kilometers in altitude. The first launch took place on October 21st, 1961. It failed. Instead of dispersing into a uniform cloud, the needles clumped together into a few tangled masses. A malfunction in the dispensing mechanism allowed metal-to-metal contact before the naphthalene fully evaporated. In the vacuum of space, some needles cold welded together, forming useless clusters instead of a reflective belt. Engineers studied the failure and redesigned the system. On May 9, 1963, a second payload launched aboard Midas 6. This time, the needles dispersed properly. Within days, they began spreading along their orbital path. 5 days after launch, engineers attempted the first communications test. Using 2 large microwave dish antennas, they transmitted voice signals from California to Massachusetts, bouncing them off the needle cloud. The connection worked. The signal was described as intelligible. Data rates reached around 20,000 bits per second, roughly equivalent to an early dial-up modem. For a few brief weeks, Earth wore a working copper necklace that reflected radio waves exactly as the engineers had predicted. The reaction from the scientific world was immediate and furious. British radio astronomers and the Royal Astronomical Society issued formal protests. They feared the needles would interfere with astronomical observations across multiple wavelengths, effectively blinding humanity's view of the universe. Soviet newspapers accused the United States of dirtying space. The International Astronomical Union condemned the project, and prominent astronomer Fred Hoyle called it a major intellectual crime. The controversy escalated to the United Nations. U.S. Ambassador Adlai Stevenson had to defend the decision to surround the planet with copper wire. He cited scientific studies showing that solar radiation pressure would gradually lower the needle's orbits, causing them to burn up in the atmosphere within about 3 years. The protests continued, but formal condemnation was avoided. Still, the political fallout had lasting consequences. The outrage helped shape consultation provisions in the 1967 Outer Space Treaty, establishing that nations must consider how their space activities affect others. But by the time diplomats were arguing, the project was already becoming obsolete. On July 10, 1962, nearly a year before the successful needle deployment, the United States had launched Telstar-1. Telstar was everything Project West Forward was not. Instead of hundreds of millions of passive reflectors, it was a single active satellite weighing just 77 kilograms. Instead of merely bouncing signals, it received them, amplified them billions of times, and retransmitted them on a different frequency. Within 13 days of launch, Telstar relayed the first live transatlantic television broadcast. The U.S. Vice President made the first satellite phone call. Faxes, data, and live video began flowing across oceans with a clarity West Forward could never match. The contrast was devastating. Telstar cost about $50 million and delivered immediate, reliable, high-bandwidth communications. It could be upgraded, replaced, and improved with each generation. Project West Forward offered lower data rates, required massive ground antennas, and would need constant replenishment as the needles burned up in the atmosphere. The space age had simply moved too fast. Active satellites had made passive reflector systems obsolete before they could prove their long-term value. Plans for permanent communication belts were quietly abandoned. Project West Forward became another technology that worked exactly as designed, but arrived too late to matter. Most of the properly dispersed needles eventually re-entered the atmosphere and burned up harmlessly. But the clumps from the failed 1961 launch did not. They were too large for solar pressure to move significantly. They became permanent debris, silently tumbling through orbit. By 2020, NASA was still tracking dozens of these clusters. Some estimates suggested over 40 clumps larger than 10 centimeters remained in orbit, along with thousands of smaller fragments. They are among the oldest human-made objects still circling the Earth. The irony is hard to ignore. The same MIT Lincoln laboratory that launched the needles now operates radar systems used to track them. The technology built to protect communications also monitors the debris created by its own experiment. There is an even deeper irony. The protests against Project West Forward established arguments that still shape space policy today. Astronomers in 1963 warned about orbital pollution, interference with observations, and unilateral decisions in space. Those same concerns appear almost unchanged in modern debates over satellite megaconstellations. At the Smithsonian's Udvar-Hazy Center, a West Forward dispenser now sits quietly on display. Visitors pass it on their way to more famous artifacts, rarely stopping to consider its mission. 480 million copper needles were launched into orbit because military planners feared losing contact with their forces overseas. Today, it sounds absurd. In 1958, after a nuclear test had silenced communications across an ocean, it seemed like the only rational solution. Project West Forward succeeded at almost everything, except its purpose. It proved that passive reflector belts could work. It showed that millions of objects could be deployed in orbit. It demonstrated that radio signals could bounce off artificial structures in space. It also proved something else, that active satellites were far superior, that international cooperation was essential in space, and that debris created in orbit could last far longer than anyone expected. Most of the copper needles are gone, burned away in the atmosphere, but the clumps remain, silent and persistent, circling the planet. They are monuments to a different era. An era defined by the fear of nuclear silence, when engineers believed the only way to keep the signal alive was to scatter 480 million tiny antennas across the sky. Somewhere above us, at an altitude of 3,500 kilometers, those clumps still orbit in darkness. They will outlast everyone who launched them, everyone who protested them, and everyone who remembers why they were placed there in the first place. In more than 60 years, no nation has attempted anything like it again. The question is whether that restraint comes from wisdom, or simply from the absence of the kind of fear that once made such an idea seem reasonable.